For fun, then, you can just watch me wing it for 5 minutes on 36. It's elastic, which means what, Noah? I have an elastic collision. That's the opposite. Inelastic. Close. Elastic is maximum stretchiness, bounciness. How would you express that in like physics terms? Momentum, energy, velocity. Is transferred to the other one. Okay. Yes, that's true. But that's true of almost every collision. The only time momentum wouldn't be conserved if we produce some heat somehow, which we usually don't bother with. I've never seen them do that in AP physics. They heat up. You've lost momentum to the molecules. Okay. Peter, what do you think? Elastic is a special type. Where, let's see. Okay. 36 is trying to see how good we really are. But so 35, like these are easy problems, and if you don't have enough practice, I can always break out my, you know, Big Bang Theory quiz from honors and stuff. Sure, okay. One thing hits another. It doesn't even have to touch. We've got magnetic carts there transferring momentum. Okay. Momentum is conserved. Elastic is a special type where the kinetic energy is also conserved. We should say kinetic total before equals kinetic total after. And I use the prime for after. Well, actually, that's not so hard. We did our little derivation. We had to figure out, we had the difference of squares and divide by it, and we get a simple formula back on Monday. So if we just have momentum conserved and we have kinetic energy conserved, that's still a relatively simple formula. It had like 4 different terms, but we can figure them out and find it. Okay. However, so puck 1 is originally at rest. So here's number 1. It has mass m. It has v0x equals 0 and v0y equals 0. Oh no. Puck 2 has an incoming speed of 6 and scatters at an angle of 30 degrees. Okay. So, what that means is, here we have number 2. We'll draw a line through number 1. And we'll give v0x equals plus 6. Thank goodness they have the same mass. But then, afterwards, how should we describe after? Oh, let's make them dots after. That's what a physicist would do. Here's puck 2. It's moving at an angle of 30 degrees. So, v prime, oh, I had v zeros. Let's not do v zeros, yeah. After, I have vx equals, yeah. You could say v prime if you want, times cosine of 30, and vy equals whatever v prime is, yeah, we'll have this as v prime. The after velocity, v prime sine of 30. Okay. Now, can mass 1, it's a 2D collision. Can mass 1 still be on this line where it started? Okay, excellent. Why not? Okay, I have a positive Vy here, so I have to have, that was mass 2, we have to have mass 1 times v1 after, and then it could be some other angle, sine of something, and that has to equal, momentum has to be conserved on the y-axis. So I have to have, yeah. We shouldn't even write it like that. We should write minus, because it's going to point down. Thank goodness the ends are the same. Minus mass 1 v1 prime sine of whatever angle it ends up with, plus mass 2. Think about what if the masses weren't the same. Oh, we'd be in big, big trouble. I wouldn't assign this problem at all. This time I think you can do it with help. But if they had different masses and still elastic and still momentum conserved, oh man, that's another hard problem on top of it. Why did I do that? Oh yeah. So we have some negative momentum down for mass 1 and then mass 2 v2 prime, let's call that v2, yeah, v2 prime sine of some other angle. Oh dear. Okay, and we have and here's why you would have like a week to do this homework problem. So you would have mv0x equals mass 1. They're actually the same, but it would be mass 1 v1 prime cosine of some angle plus mass 2 v2 prime cosine of 30 before and after. So actually, oh look at that. If you could figure out those velocities, you could immediately figure out the angle. And you also have the total kinetic energy is conserved before and after. Well, before you just have 1/2 mv0x squared. And I would actually use numbers. Like it doesn't give you the mass. Use 1 kilogram. So 1/2 mv squared is 18 joules. So you have 18 joules of kinetic energy to start. Whatever it comes afterward has to be 18 joules. If you really want altitude, because that's what it's, yeah, elastic means the kinetic energy before and after are the same. It's perfectly, it doesn't, that's right, that was the deal with last year. It's hard to remember. There's inelastic where you've just lost some kinetic energy. There's perfectly inelastic. That's what Noah described, where they actually stick together. But then there's just plain elastic. It doesn't need to say perfect or completely elastic. Elastic means you don't lose any kinetic energy. Let's see. So that's the setup for the problem. You have momentum conserved in each direction, and you have total kinetic energy conserved. So you can't conserve kinetic energy just in the x direction or the y. You had some kind of split. And I think there's actually, I don't think I'm up for it this year. There's a crazy proof that I sometimes do that shows that these angles in a glancing collision actually have to add up to 90 degrees. If that one shot that way and that one shot that way, there should be 90 degrees between them somehow. Okay, and we'll do some support. Any questions? You can at least get started. Okay. I give more hints than that, usually. Alright, so 35, 36. You can get up to starting 36. After that, it jumps to 44. 44 is actually not so bad. They tell you the angles, or they tell you everything but the angle. And you can assume that these nuclear reactions are elastic. Kinetic energy is conserved as well. So it's just crunching some numbers. So 44 looks hard. It looks as bad, but it's really not. Okay. And then billiard balls again. Okay, 54, not so bad. Okay.